you ate this lunch, you know you'd be getting energy from the food, but you'd also be getting a different kind of energy. Something on that table is sending out invisible energy detected by the probe. The radiation seems to be coming mostly from the bowl with the fruit in it. Is it coming from the fruit or the bowl? The energy is coming from the bowl. Put it to one side for the moment. Even with the bowl gone, you're still exposed to this unseen radiation. Every day of your life, no matter who you are, where you go, or what you do, you're bombarded by it. It's a part of the natural environment and has been since the beginning of time. You're going to investigate this invisible, everyday radioactivity. These three discs are the ABCs of the radioactivity in your daily life. The different radiations they give off are known by the first three letters of the Greek alphabet. Alpha is the radiation coming from polonium-210, a radioactive element discovered by Madame Curie in 1898. Atoms of the polonium-210 are spontaneously giving off alpha particles, which are entering the probe and triggering pulses of electricity inside. The current is amplified by the instrument. You can see the flow of current on the meter calibrated in counts per minute. Each burst of current makes a clicking sound come from the speaker. You've probably heard the instrument called a Geiger counter. Put a piece of paper between the polonium-210 and the probe. The current drops, showing the paper has blocked the alpha particles. Nuclear researchers have found that alpha radiation is made of subatomic particles that can be stopped by such things as a sheet of paper, your skin, and other relatively thin materials, such as air. Beta, the second Greek letter, is the name given to the radiation coming from strontium-90, an element chemically similar to calcium. The betas are also picked up by the probe and register a little less than 200 counts per minute on the The paper that stopped the alphas has little effect on the betas. They go right through it. Research has shown that betas are also subatomic particles, but have more penetrating power than alphas. Now put a 3/4 inch thick piece of wood in the path of the betas. The wood absorbs most of the betas. Beta particles are stopped by such barriers as wood, thin sheets of metal, walls, and many other materials. And finally, the third kind of radiation. You may have heard of Cobalt-60 in connection with cancer treatment. The atoms of Cobalt-60 give off beta particles and a different kind of radiation called gamma, the third letter of the Greek alphabet. The combination of betas and gammas results in 300 to 400 counts per minute. Bring in the same paper. The radiation from Cobalt-60 goes right through it. Next, the wood. The Cobalt-60 betas are absorbed by it, just as the betas from strontium-90 were. Now you're measuring only gamma radiation. This is a 1-inch thick barrier of lead sheets. Most of the gammas are absorbed by the lead, as the meter shows. Almost all of the radioactivity in your everyday life is made up of these three kinds of radiation. Alpha particles, which are stopped rather easily, beta particles, which are at penetrating power, and the highly penetrating gammas. Which kind of radiation, alpha, beta, or gamma, is coming from the bowl? The sound tells you that the bowl is highly radioactive. Alphas, betas, or gammas, or a combination of them, are entering the probe at the rate of about 425 counts per minute. To find out what makes the bowl so hot, fasten the probe to the case. Next, put it on a block so that the probe is held at a fixed distance above the bowl. The alphas will be stopped by the paper. Because the count per minute drops slightly, you can suspect that some alphas are shooting out from the bowl. Now for the wooden beta barrier. Obviously, most of the bowl radiation is made up of betas. The remaining radiation is probably gamma. The lead blocks almost all the rest of the radiation, indicating it is gamma rays. What material in the bowl is giving off all this radiation? The alphas could be coming from polonium-210 in the bowl. Strontium-90 could be the source of the betas. Both betas and gammas could be supplied by Cobalt-60. But other radioactive sources also give off alphas, betas, and gammas. Uranium emits all three. So does radium. Finding out what kind of radiation is coming from the bowl or any other radiation source is only the first step in identifying the actual source of radiation. To pinpoint the specific radioactive material in the bowl, you'll need an instrument known as a scintillation counter connected to a multi-channel analyzer. It may look complicated, but the principle on which it works is easy to understand. Its probe detects only gamma radiation. At the bottom is a thin metal shield which gammas can easily penetrate. Inside is a crystal that reacts in a peculiar way when it absorbs gammas. This is not the crystal. It's a circle of tissue paper that represents the crystal. The projector will be the source of gammas. The light represents the gamma radiation. When gammas are absorbed by the crystal, some of the energy is converted to light. Not a steady beam like this, but short flashes of light, more like this. Scintillation means flashing in Latin. The light produced is picked up by a special photocell that converts some of the light energy to an electric current. In this model, the light sensing cell is similar to that in a photographic exposure meter. In the actual scintillation counter, it's a photomultiplier. The current generated by the photocell makes the needle of the meter move. Notice there's a pulse of current for every flash of light produced by the gammas. If you turn up the brightness of the projector to represent gammas of higher energy, the flashes of light they produce are brighter. The higher energy generates a stronger current. Each pulse of current is in direct proportion to the energy of each gamma. Now let each burst of current be represented by one of the red balls in the trough. Inside the scintillation counter is a memory. That's what those channels on the lower right are supposed to be. The value of a given pulse of current is stored in the appropriate channel. The The energy of each gamma determines where the information is filed. As more and more gamma energies are measured, the data in the memory begins to show a pattern. Scanning the channels now shows that most of the gamma energies had a value of 8 in this model. Of course, there are no balls inside a real scintillation counter. It's a highly sophisticated electronic device for detecting, measuring, storing, and displaying gamma energy patterns. Now that you know how it operates, you're ready to use it to measure the energy of the gammas from Cobalt 60. The instrument is all set. The gammas are penetrating the crystal, generating flashes of light that are picked up by the photomultiplier. Each burst of current is being measured and then displayed as a tiny dot of light on that round screen. The dots that represent the gammas of the same energy are added together like the balls in the slots. Gradually, the pattern formed by the Cobalt 60 gammas develops. Here's a photographic record of the Cobalt 60 gamma energies. Later, you'll compare it to the gammas given off by the ball. What do you suppose the curve for uranium will look like? You'll soon see for yourself. Uranium gammas are creating flashes of light, which are changed to bursts of electric current that will eventually show up on the screen. The gamma radiation from uranium produces a pattern. Here's the photograph of uranium gamma energies. Note how different the pattern is from that of Cobalt 60. Now to check the gamma radiation from radium. This is the photograph of the radium gamma energies. Compare it to the others. Remove the radium source and put the bowl under the probe of the scintillation counter. If you suspect that it contains Cobalt 60, uranium, or radium, you're right, it does. But which one? Measurement of the gamma energies coming from the bowl will give you the answer. As soon as the bowl gammas have been measured and stored, you can compare them to the patterns of the gamma energies from Cobalt 60, uranium, and radium. Here's the photograph of the bowl gammas. Is it similar to Cobalt 60? Uranium? Or radium? The pattern of the gamma energies from the bowl matches those of uranium, so the bowl contains radioactive uranium. The orange glaze on the surface of the bowl contains uranium ore, which was once mined for its color. The ore contains radioactive uranium-238 in it. Today, dishes like this are no longer made in the United States because the radiation from the uranium was found to be potentially dangerous. Uranium is now mined for use as fuel in nuclear reactors that power ships and submarines, as well as generating plants that can produce enough electricity for millions of people. For many years, the dials of watches and clocks that glow in the dark like this were coated with radium. Radioactive tritium is now used instead of radium. Radium has proved to be an effective treatment for certain types of diseases. Other ordinary things are also radioactive. This is a mantle for a gasoline lantern. It's slightly radioactive because it's coated with thorium-232. The burning gasoline heats the thorium, producing a brilliant light. Scientists have discovered radioactive elements in many more everyday objects besides uranium bowls, radium dial clocks, and thorium mantles. They found, for example, that you're exposed to a very small amount of low-energy radiation every time you watch television. Not very much, but a measurable amount. The radiation you receive when you watch 1 hour of color television each day in the year can be considered a sort of unit of exposure. 365 hours of watching color television will then have a value of 1. If you live in a wooden house, you receive about 17 TV units of radiation each year from natural radioactive materials in the wood. Bricks are even more radioactive. In a brick house, you get approximately 36 TV units in a year. Everywhere you go, you're bombarded by what is called cosmic radiation. Scientists have identified it as radiation coming from the sun and outer space. Some of it can penetrate the atmosphere, buildings, and people. At this very moment, some of it is going right through you. If you live at sea level, the cosmic radiation you get in a year is about 20 times what you receive from watching 365 hours of color television. 200 feet above sea level increases your cosmic radiation by about 1 unit each year. A 10-day vacation high in the mountains exposes you to cosmic radiation of 1 more unit. The ground you walk on is also a source of radiation, adding 7 1/2 TV units a year. Minute amounts of these radioactive elements are taken up and stored by plants. Cereals, Brazil nuts, and tea are some of the plant products that are relatively high in these elements. Animals eat the plants and concentrate the radioactive elements in various parts of their bodies. You're exposed to some of this plant and animal radioactivity in the food you eat, and more in the water you drink. On the average, food and water add 12 1/2 TV units of radiation a year, mostly beta and gamma. You and the people around you give off measurable amounts of beta and gamma radiation. Even the air you breathe is slightly radioactive, giving off alphas, betas, and gammas that add 2 1/2 TV units per year to your total. Nuclear power plants are a source of radiation to people who live near them. Assume you spend 24 hours every day in the year at an average of 5 miles from such a power plant. The radiation you'd receive would be equal to about 1/40th unit, about 8 days' worth. A single dental x-ray exposes you to 10 TV units. A chest x-ray averages about 100. Medical x-rays expose you to more radiation than any other source. Not including x-rays, the total amount of radiation you get in a year averages about 100 units, as much as watching color television for 100 years. Even without the uranium bowl, the food you eat, the water you drink, the air you breathe, expose you to radioactive elements. Radiation is emitted by almost everything around you. Now you know that no matter who you are, where you go, or what you do, you are constantly bombarded by the alpha, beta, and gamma radiation that's a natural part of your environment. Your everyday radioactivity.